So thank you very much for the invitation. So this is a joint work with Milton Jara and Patricia Gonçalves from Rio. And in this talk, I would like to speak about superdiffusion of energy in the chains of oscillators. So the general motivation is the usual motivation of statistical mechanics. So we want to derive macroscopic equations starting from microscopic dynamics. And maybe the simplest equation that you can imagine, the macroscopic equation, is the heat equation, which describes the evolution of the temperature in some macroscopic system evolving in time. So just this equation, whereas the time evolution of the temperature is given by the gradient of the conductivity times the gradient of the local temperature. So this is a very simple macroscopic equation, but I don't want to discuss really this equation, but some other equation, which is a fractional heat equation, because in some there exists some microscopic system like carbon nanotubes, in which you observe that the diffusion is anomalous, so you don't expect to see the heat equation, but something else. And so the heat equation is not the correct macroscopic equation which will describe the macroscopic evolution of your system, but you have to decide what is the macroscopic equation which should replace the heat equation in this context, in the context of system which have some anomalous energy diffusion. And E.
It's the last.
Sorry. What? No.
It's only one T, not two T's.
He's correcting your spelling, which is.
Literature. Okay. Sorry. Yeah. Okay. So there is some debates about what is this equation, this macroscopic equation, which will replace the heat equation, and so the usual microscopic models which are used to describe heat conduction in solids are given by long chain of oscillators, of coupled oscillators, so which are just Hamiltonian system, whereas Hamiltonian is, so here I consider only one-dimensional system, because it is for one-dimensional systems that you expect to see some anomalous energy diffusion. So here you have some atoms which are distributed on the lattice, Z, and on each side, X, you have a particle with some momentum which is denoted by Px, so all the masses are equal to 1, and you have some interaction potential between the particle, which is just a function of the interdistance particle between nearest neighbor particles. So Qx here is the position of the atom X, Rx is the elongation or the interdistance particle between the two particles, and so you have here the interaction energy and the kinetic energy. So this system evolved with Newton's equation corresponding to this Hamiltonian, and you can show that the dynamics is well defined, at least for a lot of potential V. And so since you have some Hamiltonian system, you have some conserved quantities, and among the conserved quantities, maybe the main important conserved quantity is the energy H, which is just the sum of the kinetic energy and the interaction energy. But you can also have other conserved quantity like the total momentum, because here you don't have spinning on the particles. So the total momentum is conserved by the dynamics. And you have also a third quantity which is sometimes forgotten, which is the total length of the system, which is a trivial conserved quantity, which is just so if you write it in terms of the Qx, it is a trivial conserved quantity. But nevertheless, it is some quantity that you have to take into account. And
Any boundary conditions?
so here I have in the infinite lattice, so you don't have any boundary conditions. So otherwise, it is okay if you can consider also periodic boundary conditions, but these conserved quantities are conserved in the bulk of the dynamics. And of course, there is a very challenging problem, which is to decide if these conserved quantities are the only one, or if you could have some other conserved quantities. And we know that for some particular potential it is false, we can have all other conserved quantities. For example, for the harmonic chain, when V is quadratic, we know that there are an infinite number of conserved quantities. But for example, if you take V in some exponential form, you get the total lattice, and in this case, you have some integrable, completely integrable system some infinite number of conserved quantities. So this is a very difficult problem to know if you have only these three conserved quantities or if you have some other conserved quantities. And nevertheless, if you assume that these conserved quantities are the only one when the system is very large, what you expect is that if you look at the system in the Euler time scale, you should observe some evolution of the empirical energy, the empirical momentum, and the empirical compression when you perform some scaling limit. So in the Euler time scale, you expect that the following Euler equations.
Euler time scale means that you have same scaling for position and time.
Yes, exactly.
Not everybody.
Okay, so it is some hydrodynamic limits. So I rescale space by some factor n, and I accelerate time by factor n also. And in this case, if you look at the empirical energy, so in some small box around some microscopic point x at time t, and you do the same for the momentum and the compression, what is expected is that the evolution is described by the Euler equations. And here in these Euler equations, so you have just the variation of the elongation is given by the momentum, the derivative of the momentum, and the time derivative of the momentum is just given by the derivative of what should be interpreted as the pressure tau, which is a function of the elongation and the energy and the momentum. Okay, and you have some evolution also for the energy. So this is just the Euler equations for lattice gases. For harmonic coupled oscillators. So now there are some interest in so this is the first description of the system in some time scale. But what we like to do also is to study the fluctuations, not only some kind of hydrodynamic limits, but also the fluctuations of the conserved quantities at equilibrium. So imagine that you start from some Gibbs measure at equilibrium at some temperature beta and with some pressure tau. You would like to study the correlation function at different time and different position of the conserved quantities. So here, G is just some vector representing the position, the interdistance particle, momentum, and energy. And we study the correlation, the space-time correlation of these conserved quantities. And under the Gibbs equilibrium measure with temperature inverse temperature beta and pressure tau. Okay, so the Gibbs measure is indexed by 2 parameters. And so recently, Albert published a paper where he used what he calls the nonlinear fluctuating hydrodynamics to predict the behavior of his large time behavior of his quantities. And so these nonlinear fluctuating hydrodynamic predictions are based on the fact that in some constrained time scale, your microscopic dynamics can be described at the macroscopic level by the Euler equations. And then, so what he claimed is that by using this theory of nonlinear fluctuating hydrodynamics, he can decide the behavior, he can give the behavior of the correlation function of the different conserved quantities, and he is able to identify several classes. Among them is the Kardar-Parisi-Zhang universality class, but you have also some other universality classes which appears. And so these predictions are just based on some macroscopic description. So you just assume that your system can be described at some macroscopic time scale by the Euler equations. And just with this information, a priori you can derive the behavior of these correlation functions. And so in fact, this approach has been written for the harmonic chains of oscillators, but it can be applied for any conservative system whose conservative fields evolve in the Euler time scale according to a system of conservation laws for 2, 3, or more conservation laws. And in this case, you have different classes, but the same picture holds. So now this is a non-rigorous predictions. And so mathematically, there is a lot of work to do to really prove these kind of behaviors. And since it seems very difficult for purely Hamiltonian system, what we do is that we introduce some noise in the system. So this idea is to introduce some conservative noise, so conservative in the quantities you are interested in, so has been probably for the first time given in this paper by Stefano and Diao for in the context of real gases, and also there is also some work related by Joel for the chains of oscillators. So the idea is to introduce some noise which should simulate the nonlinearities of the system. It should help to prove something mathematically. Okay. And in particular, in this paper, what is proved is that if you add some noise, then in the hyperbolic time scale, you can derive, before the shocks at least, the Euler equations. Okay? So this is the first step, which is where you have a rigorous proof, something which is missing for purely Hamiltonian systems. And so it is a good starting point.
So the other, yeah, of course, the other equations you're looking at are always compressible, right?
Yes, compressible, yes. So
we're still at this first stage.
Yes.
We haven't gotten very much further since 93.
Okay. So now what we do is that I will discuss in this talk, so these chains of oscillators where I introduce some noise in the dynamics in order to have good ergodic properties and try to say something about the predictions of the nonlinear fluctuating hydrodynamics. So what we do is that we start with the harmonic chain. So harmonic chain is a very bad model of heat conduction, since we know that it is without noise, it is completely integrable system, and the energy travels the chain ballistically, so it is not a good candidate. But anyway, if you add some noise, you can expect that it should simulate some real anharmonic chains. So I first start to write the harmonic chain in a with different variables. So I just perform some trivial change of variables. So I just introduce this dynamical variable eta x, where for even sites, it is just the momenta, and for the odd site, it is just interparticle distance. Okay? And then if you use these variables, you can rewrite the Newton's equations corresponding to the harmonic chain in this simple form. Okay? This is just a rewriting of the Newton's equation. Now I introduce some noise, and the noise will mix the P and the R in order that it conserves the energy and some other conserved quantity. So what is the noise? So imagine that on each bond x plus 1, what you do is that you put some Poisson process with intensity 1. So all the Poisson processes are independent. And between two, so you can see the Poisson process as a clock. And between two successive rings of the clocks, what you do is that you let the dynamics evolve according to the Newton's equation. So according to this just deterministic dynamics. And when the clock rings, what you do, when the clocks of the site x plus 1 rings, what you do is that you exchange eta x with eta x plus 1. Okay? So in this way, you say that you conserve the energy. So I hope that the dynamics is clear. Okay? Just between two successive rings of the clocks, what we do is we let the dynamics evolve according to the Newton's equation, which are written here. And when a clock rings, what we do is that we exchange eta x with eta x plus 1.
I'm sorry, you don't have the potential, doesn't enter Newton's equation?
No, here it is just the harmonic chain.
Oh, you're going to just harmonic chains.
Yes, so it is the reason for which it can be written this way.
Are you going to be able to do all this in higher dimensions too? Like this is one dimensional, I see.
Okay, the problem of anomalous diffusion is restricted to the one-dimensional case.
So you're not going to have anomalous diffusion
In 2 dimensions, you have also some logarithm divergence of the conductivity and so on, but the real interest in dimension 1. So, but otherwise, you could define the dynamics in higher dimension.
The same construction.
Yes. Okay, so you see now you have some Markov process which is well defined, and this Markov process conserves the energy. So the energy with these new variables is just the sum of the eta x square, okay? Because eta 2x is px and eta 2x plus 1 is just rx. So here you have this equality, and you see that when the dynamics evolve according to Newton's equation, this quantity is conserved, and when you exchange eta x with eta x plus 1, you don't modify this quantity, so it is conserved. And nevertheless, the noise is bad because it destroys the conservation of the momentum and the conservation of the completion field, okay? Because the sum of the eta 2x is not conserved, nor the sum of the eta 2x plus 1 is not conserved by the dynamics. Nevertheless, so the volume field, so I called it volume because I have to find some name. So eta x, the sum of the eta x is conserved by the total dynamics. It is conserved by the Newton's equations, and it is also conserved by the noise. When you exchange eta x with eta x plus 1, the sum of the eta x is still conserved. And in fact, this quantity, which is the conservation of this quantity, will be responsible of the anomalous diffusion. It is because it is conserved that you have some anomalous diffusion. If you introduce some noise which conserves the energy but destroys this conservation field, then you don't have anomalous diffusion. Okay, so this is the dynamics that I will consider. Harmonic chain plus noise, so noise conserving 2 quantities.
So if it conserves energy, and I guess I don't quite understand this last line there.
So the sum of
The sum is conserved.
yeah, the sum is conserved.
The sum is conserved.
Yeah, the sum, yes. Okay, so you have 2 conserved quantities. And this noise is introduced. In fact, we could consider some other noise. Some noise we exchange, for example, only the momenta, px with px plus 1. And in this case, it will conserve the three quantities, the energy, the momentum, and the sum of the Rx. But we decided to consider this noise just to simplify the computations, because in this case, we have only 2 conserved quantities, and it is easier. But in fact, we could derive the similar results for a system with 3 conserved quantities with a different noise. But it is just simplification. Okay, so I say that the volume and the energy are the only conserved quantities of the model. And in some sense, it can be precise, and it is really, there is some theorem behind, which is essentially contained in the paper of Joel and Fritz and Funaki, where you can show that this is the only conserved quantities. And since you have only 2 conserved quantities, you have some Gibbs measures, which are parameterized by 2 parameters, tau and beta, so which are just product Gaussian mergers. Okay, it is just inverse temperature beta and the pressure tau. Okay, and these mergers are, of course, invariant for the dynamics, and the system is non-reversible with respect to these dynamics. And now we are interested in the fluctuation, the correlation function at equilibrium for the conserved quantities, for these 2 conserved quantities. So if you first look at the system in the Euler time scale, when you perform, so you rescale space by a factor n, and you accelerate time by a factor n, then you can see that the 2 conserved quantities, the volume field and the energy field, the empirical energy field and the empirical volume field, evolve according to these 2 equations. So this is just a very simple equation because we are in the harmonic case. So here, in fact, these equations are well defined for any time. You don't have shocks. Okay.
So V is Rx
plus Px. Rx plus Px.
plus Px.
You can see it like that. So it is not really a physical physical quantity. Okay, so by using the relative entropy method, we can show these that in the Euler time scale we have these two equations. And of course, this is true only because we have the noise. Without the noise, we know that for the harmonic chain, we don't have any chance to derive some microscopic equations. Okay, so now what we are interested in is in this correlation function of the energy. So the average, so we start with the dynamics at equilibrium, and to simplify, I just take the pressure equal to 0. Otherwise, you have just to translate the dynamics by the constant tau, and then you have exactly the same evolution. So you can assume tau equal to 0 for free. Then we are interested in this space-time correlation and the long-time behavior of this space-time correlation that I denote by STX. Okay, the correlation function.
So are you interested in fixed x, large t, or are you going to do?
Well, for the moment, it is defined for any t and for any x. And now it is a theorem. So what we do is that, so you look in a longer time scale. So you take, okay, so you take two smooth functions of compact support, and you rescale space by some factor 1 over n. Okay, and then you look at the correlation function in a time scale of order n power 3 half. So if you add some normal diffusion, the correct time scale will be Tn squared. The fact that you have a Tn 3 half means you are in a subdiffusive time scale, so it means that you have superdiffusion of energy.
So, to go back to the microscopic equations, rescale, you forget about the Euler scaling.
So you mean these macroscopic equations?
This is under Euler scaling.
Yes.
Yeah, so
But then it's the next thing, you forget about
Yeah,
Euler
yeah.
scaling. You have different scaling.
Yes. Yes.
That's all.
no,
You don't
In fact, it is the
follow
fluctua-
Euler and then do something
That's right.
else.
No,
this
it
is
is.
directly on the
Yeah,
on the
that's
equation.
Yes, it is in equilibrium.
Do your Euler equations already have the 1/3, 2/3 scaling inside them?
No, so the scaling is the Euler times the Euler scaling.
So this, you have two
Does this
different
equation
series.
rescale at the scale that you had fluctuations already exact?
Speak louder, Jeremy, I can't hear you.
Sorry.
No,
Sorry.
I don't understand the question.
You rescale the whatever it is, the German V and the German E with this n to the 3 halves and the n, like you're rescaling the correlation function. Is it invariant?
No,
This equation invariant under this 2/3 scale.
no,
The Euler equation.
no, I don't think so. No. So in fact, here it is a law of large number, and what we are studying is
We're doing
So-
fluctuation?
yes,
So it's
the
not
fluctuations.
Not captured by this, right?
Yes. So you see here we have this factor 1 over n, which has to be, since we are taking in fact the variance, it is, you have to look, in fact it will be clearer later, but it is like 1 over square root of n square. So because you take the fluctuation field, the variance of the fluctuation field. Okay, so I will precise a little bit later, but what is the theorem? So the theorem says that in the large time scale, okay, the correlation function are described by some macroscopic object, which is this kernel, Pt, and this kernel is given by the fundamental solution of the fractional equation, which is given here. Okay, so you have some. So if you had normal diffusion, what you would expect is that if you multiply here by n square, not n 3 half, but n square, you will get to the same so the phase integral, but with Pt replaced just by the Gaussian kernel. Okay, so here we identify the limit. We identify the limit, and we say that is a fractional Laplacian with a special value of the exponent, which is 3 over 4. And we studied the correlation function for the energy, but we can do also the same for the volume field, which is the second conserved quantities, and we can show that the volume field does not evolve in a strange time scale, but in the diffusive time scale. So the volume field has normal fluctuations. It is only the energy field which has strange fluctuations, anomalous fluctuations.
I go back to my earlier question. Is there any analog of this in higher dimensions where you replace the end of the 3 halves by some logarithm?
So you mean here? Or?
Yeah.
Yes, it is invariant for this. So it is scaling. It is invariant by the scaling where you multiply the space by epsilon and the time by epsilon minus 3 half, or something like that.
He's asking
Yes.
do you get a log scale? The same equation you get log scale.
So, okay, I don't know. It is really something that we expect to hold only in dimension 1.
You got some anomalies. Questions can be, if you understand the anomalies in 2 dimensions too. There's some kind of anomalous behavior, I suppose.
I think from the fluctuating hydrodynamics, you would get normal in 2 and 3 dimensions.
Logarithmic corrections, but
Mhm.
in 2 dimensions you get logarithmic
I would expect so.
Yes, in 2 dimension.
This is really one.
Yeah.
Can you check that the field itself is Gaussian too, or just because?
For the volume field, you mean?
Like this one, or whichever one.
So for this one, just
I don't know.
What's the question?
It's Gaussian.
Yes, I don't know.
Hmm?
This
That
is
was
the
the
covariance. The question is whether statistics is Gaussian actually. But the statistics is Gaussian. That's just the covariance. And that's a good question. Do you expect it to be Gaussian?
If I expect, I don't know. I don't think it is Gaussian. No, a priori, why it should be Gaussian? I don't know. Do you expect it? Okay. Okay, and I just say that these results are in agreement with the nonlinear fluctuating hydrodynamics. So the nonlinear fluctuating hydrodynamics can be applied to any system which in some coarse grain time scale is described by some system of conservation laws. So, and if you apply the theory, you get some predictions, and these predictions are well confirmed by these results.
But if we would do the interacting case, then we would get some other scaling.
In some other potential, you mean?
No, I mean, what would you, if you do your, in the case you have interaction, so with anharmonic case,
Yeah, if you take an harmonic potential, then you would get different.
the different scaling. And what would the n if you had be replaced by?
It depends, I mean, you have several conserved quantities.
I understand.
So it just goes to do other exponents and
But the KPZ ones,
KPC would be one of them.
Yes. So it depends really on the form of his equation and the parameters which are inside. But for this system, what we expected exactly what is proved.
See, if you go back to that just a moment, you can go back to the Euler equation. See, what happens here is that the quadratic term is the v squared, I mean, which is, the one which is covered by the linear equation. If you want to get KPC, you should have the term which goes like e squared in the second equation. If you have an e squared sitting there, then the expectation is that it goes, I mean, so in some sense the leading term is missing, so, then it's this other type of separate.
So okay. So this is the theorem that we obtained. And okay. So now I would like to present you some ideas of the proof, which is in fact not so complicated. So what we are interested in is the energy field, which is 1 over square root of n, the sum over, so you take a test function f, okay, smooth test function, and you look at the fluctuation field of the energy in the time scale n3 half. And we would like to study the limit of this guy as n goes to infinity. Okay, and so what we do is we introduce what we call the quadratic field, which will be used as some tool to derive the equation for this fluctuation field, for the energy fluctuation field. So the quadratic field acts now on function of 2 variables, and what appears is the 2-point correlation function here at different sites, y and z, but in the same time scale, and for y different from z. Okay, and we'll see that there is some connection between these 2 fields. So the problem when you want to derive macroscopic equation for the energy field is that, so you take the time derivative of this guy, and you see what happens, and you want to close the equations in order to have some evolution. And when you do that, what you will see is that it will appear this quadratic field. So more exactly, if you use some Ito calculus and you take the derivative of the fluctuation field, what you have is the quadratic field applied to some function plus something which will be small, which is 1 over square root of n times the fluctuation field applied to the second derivative of the function f. So if you expect that it converges to something, since there is a factor 1 over square root of n, it should be small and goes to 0. Okay? So this is not difficult to show, in fact, that this term goes to 0. And you have some martingale term, which are also very easy to control because you can compute explicitly the quadratic variations and show that it goes to 0. So the only relevant term is this guy. So it is the quadratic field applied to a spatial function, which is in fact not a function, which is a distribution. More exactly, how is it defined? So remember that the quadratic field is defined on function of two variables, okay? Because it is a correlation between two different points. So this function is a function of two variables, and f is a function of one variable, and it is defined in the following way. So you just take the Dirac mass on the diagonal, and you multiply by the function of one variable on this diagonal. And this is how is defined this function, which appears here. So in order to understand the time evolution of the fluctuation field, you have to understand the time evolution of the quadratic field. Now you look at the evolution of the quadratic field, and what you see is that you can almost close the two equations together. The time derivative of the quadratic field is given by the quadratic field applied to some new function, which is defined here, I will precise later, minus the energy field applied to a function of one variable, but remember that h is a function of two variables. So here what we take is that we take the gradient, we take in fact the directional derivative of the function h along the diagonal. So here the vector e is just vector along the diagonal, 1, 1. Okay? And then we take the trace of the function on the diagonal, and we get a function of one variable. And it remains some remaining terms. So for example, the quadratic field applied to some function defined from h, but with some factor square root of n in front of it. So since you can expect that this guy is small, in fact, it is not so easy to show that it is small. You cannot just use like that Cauchy-Schwarz inequality to prove that it's small. You have really to work to show that it's small, but it turns out that it is small. And you have some martingale terms which are also small. Okay, and what is, so essentially everything is contained in these black equations here. So you can forget everything which is written in gray. And what is this operator Ln? It is just given by the following. It is 1 over square root of n times the two-dimensional Laplacian. So in fact, it is the two-dimensional Laplacian on of the lattice 1 over n z squared, but okay, you can take the approximation, plus 2 with a very big drift, 2 square root of n times the gradient in the 1, 1 direction along the diagonal. Okay, so if you forget all these terms, which
the second equation, is that supposed to be obvious how that comes about?
it is what?
How do you get the second equation, or are we supposed to understand that or not?
I use Ito calculus. So we have a Markov process. We have some evolution which is described, and just I take the derivative of this guy, and it is because you have some harmonic equations, harmonic interactions, that you get something which is closed. In fact, enclosed in these two fields. It is only because you have harmonic interactions. Otherwise, you will get some hierarchy.
I didn't know where the L came from.
Ln, you mean?
The Ln, yes.
So it comes from, so you have this noise which consists to exchange, and it will produce this Laplacian. And there is this gradient which comes from the asymmetric part of the generator which produces some gradient. There is, so the Newton's equations are d eta x is equal to eta x plus 1 minus eta x minus 1. So essentially this is a gradient. But here it is a function of two variables. So it is, So you have, when you apply the generator of the Hamiltonian parts on this function of two variables, since it is a first differential operator, you have the first gradient times the function plus the function times the gradient. So at the end, you will get this gradient in the diagonal direction.
That 1/8 to 1/2 term looks too big in reality. 2 minus 1/2 looks pretty severe.
Yes, it seems to be big, but in fact, what we will do is that this guy here is also big a priori, because it is not a function, it is a distribution. So we are evaluating something against a distribution, and we will choose, in fact, the function h in order to cancel these two terms. So that it's true that a priori this guy is very large, but this guy also is very large, and they will compensate. So what we do is that we choose a function hn, which is in fact a function of f, as the solution of the following Poisson equation. Okay? And we add the two equations that we have here. So if you add the two equations that we have here, and if you choose hn in this way, you see that you can cancel these two terms. And then, if you can show that qtn of hn is small, then you will get some closed equation in terms of st, in terms of the fluctuation field. Okay, so this is the strategy. We just choose a test function hn as a solution of the following Poisson equation. So hn is in fact a function of f, and then we add the two equations together, and we get some closed equation for the fluctuation field. So up to small terms, in fact, there is some more to show that these terms are small, but what we can get are the following equation with the remaining term, which is the quadratic field applied to the function hn. So if you integrate in time, and if you use just the Cauchy-Schwarz inequality and you have some control on the function hn, you can show that this term won't contribute. It will vanish in the limit. So at the end, you get something which is closed in terms of fluctuation field. So it is closed because, in fact, the function hn is a solution of the following Poisson equation. So it is a function of f. Okay? And it is quite explicit because it is just a linear operator. So you can almost solve this equation by Fourier transform. So you get the closed equation. So if you can show that we have some weak compactness and so on, you can show that you have some limit, and the limit is identified by this equation. And what remains to show, to prove the theorem, is only to show that the solution of this Poisson equation, as n goes to infinity, converges to this guy, which is the guy which appears in the limit. Okay? Because if you look here, you have st of f minus s0 of f, it is equal to minus 2 integral from 0 to t of the energy fluctuation field applied to a function, and this function is this one. Okay, and this can be shown by using Fourier transform. It is quite easy because you have some the operator ln is not too bad. It is just a linear operator, so you can use really explicit Fourier transform. And you have to control all the other terms that I said were small, and then you get the following. Okay. Okay, I just finished by some works about the same subject. In fact, so in some recent paper, so Jara, Komorowski, and Ola obtained very similar results, but for the harmonic chain, which is perturbed by the noise, which consists to exchange momenta at different the momentum of site x and the momentum of site x plus 1 at some random times. So in such a way that three conserved quantities. And okay, their proof.
What you just do is a Poisson.
Yes, Poisson process. So it is. It was the first okay, it was related to. Okay, so here, if you have a real harmonic chain, you think again harmonic chain, you have three conserved quantities, which are the following. the momentum, and the compression of the chain. And what you do is that, so you let your dynamics evolve according to the Hamilton dynamics, and when a clock rings, what you do is that you exchange px with px plus 1. So if you do that, you conserve his quantity, and you conserve also the momentum, and since you don't act on the interdistant particle, you conserve also. And in this case, so the equations are the following, and they obtain, they can show, but by a very different method, by using some Wigner transform and anti-Wigner transform, they can show that you have a similar result, but in their case, so they have the real fractionality equation. They don't have this asymmetric version of the fractional equation. This asymmetric version is in fact due to the fact that you have two conserved fields, and one of the conserved fields is the volume field. And the volume field has some speed, which give this term. But in the case where you have two conserved quantities, the momentum and the compression have two opposite velocity fields, and you have some cancellation between these two terms, so that at the end you get really the symmetric fractionality equation. But essentially the result is the same.
So what do Sylvester and Caporelli do with this?
What do I confirm with respect to the nonlinear?
What do Caporelli and Sylvester?
Okay, yes, I didn't speak about that. So this, in fact, okay, I wrote the, so I said that we have to solve this equation. So f prime times delta. And so how do you get the fractional Laplacian, for example? It is easy. What you do is that you take the half space, and you put some function f here, and you solve the Poisson equation in the following way, with the two-dimensional Poisson equation with ux0 is equal to fx. And what you can show is that the solution of this Poisson equation, so u is a function of f, and then it is just the fractional Laplacian, but power something. So I don't remember. So it is not 3 over 4, it is something else. But this is some, so, and in this paper by Caffery and others, they generalized this kind of construction to some other operators, and they can show that you can produce a lot of long-range operators by doing this kind of procedure, by taking some Laplace equation, some Poisson equation with respect to the Laplacian, but with some boundaries, and then you can get some fractional Laplacian and some other operators with long range. Okay, but we don't use, in fact, this paper. This is just a remark. Okay, now the proof is just restricted to the linear case. So in fact, if you look at the equation, we use some information of we use the fact that we had some harmonic interactions, because here we have on these evolution are closed in terms of the S and the Q. And this is due to the fact that we have linear interaction, so that we don't have a hierarchy. So if we want to adapt this proof to the harmonic case, it is clear that we will get some hierarchy, and we cannot apply directly this proof. Okay, we have to do something. But we think that the introduction of this quadratic field is interesting, and maybe by using some standard techniques of hydrodynamic limits like Boltzmann-Gibbs principle and so on, maybe we can do something even in the harmonic case. But okay, this is some work in progress. So, okay, now I would just like to finish by some work in progress, but I will present some results. I'm not sure they are correct. So it is just maybe a conjecture or something like that, because it is what I get is a bit strange and not confident in what I will say. But the problem is maybe interesting, which is the following. So we consider the same Markov process, so the harmonic chain plus some exchange noise. So we exchange eta x with eta x plus 1. So it conserves the energy on the sum of the eta x. And now we add a second perturbation, stochastic perturbation, which is the following. So with some intensity, which is small, which is of order n power minus b, where b is some parameter which is fixed, we flip independently on each inside at Poisson times the variable eta x into minus eta x. So these second perturbations will conserve the energy, but will destroy the conservation of the sum of the eta x. Okay? But since it is very small, in fact, it does not conserve really, it does not destroy really the conservation of the sum of the eta x. So in fact,
N is what here? Is that
n is a scaling parameter. So it is some big parameter for the moment. And okay, so the energy is always conserved by this perturbation, but the volume, the sum of the eta x, is not. It is only in the case where b is equal to infinity that it is really conserved. Okay. And now what we do is that we look at the system in the time scale t and a, with a which should depend on b, in order to see some evolution of the fluctuation field, of the energy fluctuation field. So the interest of this perturbation is that we would like to see some connection between the normal diffusive behavior and the anomalous diffusive behavior. Because if b is equal to 0, so if you add this flip noise with intensity 1, what you do is that you really destroy the conservation of the volume. And in this case, we can show that we have normal conduction, we have heat equation. Now, what happens if you increase a little bit b? And so the picture that we have for the moment is the following, and I am not convinced that it is correct, but I didn't see where are the mistakes, so maybe it is correct. So it seems that if you look at the time scale, so A is a time scale in which you have to look at the system to see some time evolution. So when b is equal to 0, okay, you don't see here, you have some arrows here, but okay, when b is equal to 0, so you have really a flip with intensity 1, so the volume is destroyed and the energy is conserved, you get a diffusive time scale. So it is Tn squared, and then you have the heat equation. Now,
and that's actually independent of having the other noise.
yes, it is independent of having the other noise. In fact, it does not contribute. Yes, it is true. And now we increase b. So it means that we decrease the intensity of the flip noise. And then we still get the heat equation up to a certain value of the parameter b, of the intensity of the noise. And here, so the time scale is a is given by a is equal to 2 minus b over 2. And it is only true at least we can show it up to 3 over 3, 4 over 3. We can also show that we have no evolution between 4 over 3. And if b is very large, so what we expect is that we get the fractionality equation. For b equal to plus infinity, when you don't have flip, you have the fractionality equation. And we try to reduce, to increase the intensity of the flip noise. And then we still have the fractionality equation up to a certain parameter, which seems to be 3 half. So it means that here maybe, okay, if everything is correct, so I'm not totally sure. But, it means that probably here between 4 over 3 and 3 over 2, you should have some macroscopic evolution which should describe some connection between the normal heat equation and the fractional heat equation. What is a bit strange is that what I would expect before to do the computation was the following. So heat equation up to the time scale 3 half, and then fractional heat equation 3 half. But here it seems that you have to decrease up to 4 over 3. So I don't know why 4 over 3 is so important. And then probably you have to increase the time scale at this point to go to 3 half. And this is something which is a little bit strange. So I don't really believe in this picture, but it is what the computation seems to show.
So is this an intermediate time scale statement?
Here you mean?
Yeah.
It is A is equal to 2 minus B over 2. So it is diffusive time scale here when B is equal to 0 and 2 minus B over 2. And in this case, you have just the heat equation. Okay, so I think I will stop now. Thank you very much.